Bolton. I'm the team lead for a vessel path generation tool. I'm joined by my Scrum Master, Kyan and my two Scrum developers, Coombes and Stephan Shea. Our clients are Rachel Stevens and Ian Acorn of the Naval Undersea Warfare Center. So vessel path generation tool is a utility to generate artificial vessel path data that resembles real data. Automatic Identification System, or AIS, refers to data collected by specialized sensors on board naval vessels. It includes information like the date and time the record was collected, the MMSI, which is the ship's identification, the latitude, longitude, speed over ground, course over ground, and heading. In the past, when Newark needed to test any AIS-related software, they would have to rely on using their own confidential internal AIS data. So that would cause problems with non-confidential context. So the goal of our project then is to create a source of artificial AIS data that is realistic but has no relation to actual confidential information. So some of the constraints we had to work within, we needed to use all publicly available data. It needed to function completely offline so that it could be deployed to an offline environment. And it needed to have both Windows and Linux support. The final output also had to be in a JSON file.
All right, so the high-level approach of our tool was basically to utilize a machine learning application to generate our artificial AIS data. And the way we do that is visualized here by this pipeline behind me. We start by sourcing some publicly available data from NOAA, the National Oceanic Atmospheric Administration. They're a government agency that collects information on like weather and naval commerce and that sort of stuff. We source our public data from them, and then we take that, run it through our tool to train an artificial neural network that is being trained to generate this artificial data. And then as output, we get these JSON files, which can then be interacted with graphically and plotted using our user interface. So as for some of the technologies we used Python along with TensorFlow for our generation backend. This is a pretty standard workflow whenever you're doing anything with machine learning. For our front end and user interface, we rolled with a web-based technology stack, and the reason for this was that it was cross-platform right out of the gate. As we just mentioned, it means working on Windows and Linux, and it also has the benefit that it's very, very quick to prototype and test stuff, especially when it's very visual like our project is. We use the Leaflet.js library for our plotting utilities, and we use the Node.js runtime environment for our backend server. As for some of the development tools we utilized, we used VS Code as our main IDE. The main benefit of this was that it worked very nicely with all the languages you see here on the left. For our project management, we use the Atlassian software suite. We use Google Drive for file sharing, and we use Discord and Microsoft Teams for team and client communication respectively. So the vessel path generation tool has 4 major functional components. You have the graphical user interface, you have our server, you have our data preprocessor, and you have our machine learning model. And we're going to step through all 4 of these one by one, starting with the graphical user interface, which I'm going to hand off to Chris.
All right, so our interface's main purpose is to display paths and interact with our API. So in order to do that, we have 2 main components. On the left, you have the menu over there, and on the right, you have the interactive map. The menu is a context-sensitive menu, which means the user only ever sees information that's directly related to what they're doing, and the map is made using Leaflet.js and GeoJSON files. So these are some of the context-sensitive menus you'll run across with our program. Immediately when you click on the map to generate a path, then you'll see the path generation menu pop up. That's the one all the way on the left. The path generation menu inputs the coordinates for you, and you can put in any other information you want, and then hit generate. After you've generated a path, you'll get the menu in the middle when you click on that path to select it. That's the path selected menu. From there, you can see any information about the path, and you can make changes to it as well. Then on the right, when you click on a path node, you can see all the information about an individual path node, as well as add events to that path node and see any things that you can do with it. So since plotting is such a big factor in our project, we have 3 different ways to do it. The first way is the most important way. That's by actually generating a path. So as I said before, you click somewhere on the map to have your start point, then you hit generate after putting in your information, and it'll send all that information to the backend, and the backend will create a path and send it back to the front end if you plot it. The other ways that you can put a path on the map are by either dragging and dropping an existing file onto the map itself, or by opening one from the file system. All right, the other thing we have is the path management tool. So a lot of times when you have a lot of paths getting plotted on this map, it gets confusing to manage all the information at once. So to help with that, we have this utility that you open it up and it will show you a nice table with all the information about all the paths on it at once. From there, you can filter, sort, search, anything that just isolate the information you need at a time. And it makes everything a lot easier. We also have a configuration file that holds all of the persistent settings for a vessel path generation tool. So some of the things to notice with that would be map path, which controls what GeoJSON file is loaded for the map. So that allows the user to change what map is being generated there without having to access the code. There's also visual settings in there, as well as all the events being stored in there. So this is a preview of our configuration interface, which can be used to control the configuration file. On the left, you have the config view, and on the right, we have JSON view. The JSON view is a live preview of what the changes will look like in the actual JSON file. So any changes you make in the config view will automatically be applied in the JSON view. The config view itself is actually generated by recursively stepping through the configuration file itself and grabbing every single JSON object and making a menu item for it. The reason we did it this way is because if our clients later on down the line when they're working on the project want to add settings to it, they won't have to worry about breaking our interface. It will automatically adjust for them. All right, so now I'm going to pass it off to Kyan to talk about the server.
All right, so the server is the next major functional component of our project, and it's basically the central glue that holds together all of the various different components. It's responsible for facilitating bidirectional communication between our front and back end. And at its core, what it's responsible for doing is taking the data that the user inputs on the UI end of things, pull that and push that to our Python backend, send that to our machine learning model, take the generated path that comes out of that, and then forward that back to the user interface finally for plotting and manipulation. As we mentioned before, we're using the Node.js runtime environment for our server, and we are using the Express framework in order to host it. So our front end and back end server, they're able to communicate entirely asynchronously by utilizing HX requests. The benefit of doing things this way is that we don't have to have any page refreshes or form resubmissions in order to get any updates. So for example, when the server finishes generating a path, it'll just instantaneously appear on the UI without requiring any page refresh. The server is also responsible for creating all of the child processes that execute our Python scripts and run our machine learning models. Our server is also responsible for hosting our web-based API. And essentially the way this works is that a user can go ahead and send a post request to the server saying, hey, I want you to generate me a path starting at these coordinates with these parameters 10 nodes long. And then the server will take that command, parse it, and execute it, and then you will get a JSON response back containing the artificial path data. The benefit of having a system like this is it means that you can generate our paths without using our user interface at all. And you might want to do this if, for example, you want to connect it to an existing software system, or if you want to fully automate the generation of paths. The next of our major functional components is our data preprocessor. So our data preprocessor is essentially responsible for taking that raw AIS data, which we were sourcing from NOAA, as mentioned earlier, and converting it into a format that our model is actually able to train on. The raw data that's coming in is messy and unorganized, and it's not in the numeric ranges or organizational structure that our model is actually able to train on. So we have to go through a procedure in order to prepare it. And that is a 6-step process. So the very first thing we have to do is we have to start by sorting the data into actual paths. All of the sample points that are coming in from our data set are just kind of random. Like the first data point might belong to one vote, the second might belong to another. It's just complete chaos. So what we have to do is we have to find all the data points that belong to the same vote and were collected within a similar time frame, and we logically group them as a path. Once we have our paths, we then have to go ahead and strip away any superfluous data. There's a bunch of additional information in our data set, like the vessel classification, or maybe like the crew count, for example, but that's not really relevant for the purposes of generating paths, so we just drop it from the data set. The next thing we have to do is remove what we are calling bad paths. Bad paths are paths that are either stationary, or for example, one of the AI S nodes are missing one of their sample points. So if like the third point along a path is missing a latitude, we obviously can't use that, so we just throw it out. The next thing we have to do is we have to convert all of our time information from a text-based format into something numeric that our models are actually able to work with, and we do that by parsing them as Unix timestamps. It's pretty straightforward. The next thing we have to do is we have to normalize all of our values. All of the values like latitude and longitude, they're going to be coming in like plus or minus 90 degrees or 180 degrees. However, with a lot of machine learning applications, you typically want to have your values normalized in a 0 to 1 range. And the reason for this, it's somewhat complicated, but it helps you avoid problems like exploding gradients, and generally it'll train more efficiently. But we have to normalize all of our values before we run through our training process, and we do that here. The last thing our preprocessor does, once it finishes all of these preprocessing steps, is it stores the preprocessed files as output, so we don't have to run through the preprocessor script every time we play with the model. So, onto the model itself. We had a lot of different options we could have choose from when it came to picking a model. We looked at autoencoders and adversarial nets, but ultimately we settled on what's called a LSTM, a long short-term memory model. And LSTMs are a specialization of a broader class of nets called recurrent neural nets. And their defining characteristic is the presence of this additional memory buffer that essentially makes them more perceptive to long-form time series data. Time series data is information that's just collected across multiple points over time. So for example, you could think of like the temperature as being time series data. If you took the temperature every day of the week, you have a time series sample. And that's very relevant to our project because you can essentially think of our vessel paths as time series data. Each position along the path can be thought of as just another record across the time span that is your path. These sorts of models also have the benefit of having variable length output, and they're essentially time series predictors. The user is providing the starting information for the path, and then it is predicting where the next point should go, and that is how we end up generating the paths. As for the model's configuration, it's set up as follows. We have a 6-dimensional input and output vector with several LSTM hidden layers sandwiched in the middle. The 6 input and output neurons correspond to the 6 different path features that are recorded in each of our nodes: the timestamp, the latitude, the longitude, the speed over ground, the course over ground, and the heading. All of this information runs through the hidden layers, and out the other end comes the network's prediction for the next position along the path. So you start with one point, and it outputs where it thinks the next one should go. And what we do is we go through this process iteratively as many times as we want to generate our path. We aggregate all the points together, and we have our full path. Our model is trained and optimized using the ADAM algorithm. If anyone's worked with AI or machine learning algorithms before, I'm sure you've heard of it. It's a very common algorithm used in these sorts of contexts. And the last thing of note about our model is we do not train on the absolute values of any of these parameters here. We instead are looking at what are called deltas between them. So we are looking at the differences between like points 1 and 2. Like we look at the difference in latitude and longitude over time as opposed to the actual raw coordinates. The benefit of doing this is it makes the network a lot more perceptive to how they change, and it means we get much more naturalistic curvature, for example, because the network's being forced to train on like how a path should deviate over time, as opposed to learning, oh, I need to specifically generate in this one area.
All right, so now we can show you our demo real quick. Just open that up. All right, so here's our interface. You can see there's the map front and center there. You can just zoom out a little bit to show it. And so let's say we want to generate a path. So we're going to want to click first on the map. So we'll pick a spot right in the middle of the ocean there. You can see that the points have already been put in for us because at the point we selected. We can put in a heading, length, and a likelihood. The likelihood is the percentage chance that an event is going to be generated on any given node. So then we hit generate. We left the MSI, speed over ground, and course over ground blank. Those are going to be just inserted for us randomly. That way it's a little easier to generate a lot of paths. You don't have to think about what MSI you're going to use when it has no real bearing on the results. So now we can select that by clicking on it. And we can see all the nodes on there, all the information from the randomly attached events are there. So why don't we go ahead and change its color and rename it so that it's a little more memorable and will stand out later now we have that, we can go ahead and download it to use it. All right, so let's say we already have some paths downloaded onto the system. We're just going to have to go over to the file system, open it up, and drag those onto the map itself. Now we have all these on the screen. We can click on them to select them. We can select multiple at a time to change them as a group and make edits like that. And now you're starting to see how many paths can get on the screen. It can get worse than this, but we'll want to open up the path manager at this point to better see how that works. So there you can see all the different paths that we have currently on the screen. And let's say we want to search for Jake's boat. Let's search for that, and you can find it right there. If we want to get rid of that and search for all the events that have, all the paths that have events on them, we can put into the filter over there a minimum event of 1, and it'll show up with all the ones that have events. Then we can sort those by something like their speed to find the fastest average path. All right, so that's that interface there. Now, if you want to use our API, you might have to go over to our documentation page to learn a little bit about it. So we have a documentation page built into the system. Basically, you can see everything you need to know how to use the program all coded into here. If we want to see the API specification, though, we click over there, and it'll drop us right down here, and you can see all the specifications related directly to using it. The last thing we might want to do is change some of the configuration settings. So we're going to want to go back to the main page and open up the configuration settings. And there you can see we have the map configuration settings on there and the JSON view over there. So if we make a change on this side right here, you can see the change happening right over here. All right, let's change the color of the map, and we'll add an event. So we scroll all the way down, click add event, it'll create a new one for us, and we just have to fill in the data. It's going to be called new event type, and it's going to go in the category custom events. Then we just have to hit save, and go back over to our main view, refresh the page, and we can see we're now in a new default location. We're going to change the latitude and longitude of that. We have a new color for our map, and we can go ahead and drag and drop Arnie's pirate ship back on there. Click on it, and you can see it's the same as before. But now we have a new event. So let's click on one of the nodes and add that event to it. See there's our new event type. We can add a description, and we're also able to use the add field button to add any custom metadata that you want to add. And that's stored as keys and values so it fits well in JSON format. All right, so now all we have to do is download that, and we have our final JSON output that can be used in any other software. That concludes our demo and our presentation. So are there any questions?